All right. I'm just gonna put this one more time in the chat. This is just like my GitHub repository of the slides in case you want to reference it. Yeah, let me share my screen. Okay. Where is present? Oh, good. And again, if you guys have any questions, just feel free asking, just like interrupt me. Yeah. Okay. Yeah, this is my lecture, maybe multiple parts, maybe not, but about data structures and algorithms. Okay, cool. All right. But first, time and space complexity. Can I ask if anyone knows what time and space complexity is? Does anyone know?
Is that just depends on what the gravitational pull is relative to time?
It's less like physics based, but it's more computer science based. But it does have to do with time. I mean, there is time in it, but yeah, it does have to do with time. I guess you guys can all read the slides, but basically time complexity is the time it takes for an algorithm or program to run, given a certain input. So like if I say there's like n amount of input or like x amount of input, hopefully that makes sense. Like just some arbitrary amount of input. And then space complexity is a very similar concept. It's just the amount of memory or space used by algorithm / program. So that's why we use different algorithms and different like programs and like rewrite stuff differently, because the time and complexity and space complexity are going to be drastically different depending on what you do, depending on what algorithm you use or data structure. And I think an important note to have is that time and memory are critical to make programming efficient, but memory and time often have an inverse relationship. So that means that oftentimes if you want to have a better time complexity, then you're going to have worse memory. Yeah. All right. So there's actually a way to measure runtime performance. I don't know the nitty gritty of it about it, but yeah, so there's this thing called O notation, which is the upper bound of an algorithm. So that means the worst case scenario. So like, let's say, yeah, oh, it's kind of confusing. The worst case scenario is basically all wrong things will happen, or like a certain input will be the worst possible combination, I guess, if that makes sense. And then this is theta notation. Theta notation is the middle one, and it's basically the tight bound of an algorithm. So the average case, you can think of it as the average case. And then omega notation is the lower bound, so the best case. So like if a input is sorted a certain way, then the algorithm can go super fast sometimes. And then a lot of times when people talk about O of n or O n squared, they're actually talking about theta. And then most of the time people are just going to talk about O of 1, O of n. So just using that notation. So do you guys see this chart right here? I'm hoping that you guys do. Okay. So basically, let me move this as well. Yes, so basically, as you can see, there's a wide range of time complexities. What do you guys think? Do you think this side, the right side, is the better side, or the left side is the better side? What do you guys think?
Could we define elements
Better.
here?
Yeah, like what's better? What's
oh,
better?
No. So on the bottom, like, what does
what does this stuff mean?
Refer to? Does it mean like, hey, if you have 10 billion things going on, of course your operations are gonna be slower, or is that what that is?
Yeah. You're on the right track. So basically, if you guys see on the right side, right, it says O log 1, O of 1, right?
Right.
Yeah, so what this basically means is that that basically means how fast the runtime is, right? So typically, lower runtime, so like O of n, O of log n, O of 1 are better. They're always better than like O of n kind of, or O to n to the power of n, O of n squared. So
Okay.
I'm gonna go more into explanation on the next slide. So hopefully this stuff makes more sense. But basically, what we want is a lower time complexity, right? So more so than not, we want O of n more than O of n squared, right? And then the best thing you want is O of 1, which is constant time. And I'll explain what that is on the next slide. I have too many things on my screen. Okay. Okay. Yeah, so like Chase was kind of asking about, what does this stuff really mean? Right. So runtime complexity means is basically the relationship of how fast or slow a program runs in respect to the input size. So for example, O of n means that the runtime complexity of a program has a linear relationship to our input size. So if you guys remember, linear is like, I'm doing my best example with my arm, right? Linear means that if we were to increase our data size by 2 times, then our runtime complexity of our program would also be increased by 2, right? So question, what does O1 mean? Given that context of O of n. What do you guys think? Chase, if you're trying to talk, you're muted. Oh, you're not? Okay,
I'm talking to myself, reading.
gotcha. What do you guys think? Anyone have an idea? Again, just to give some context, I know this is all brand new information, but basically it's the relationship of how fast or slow a program runs in respect to the input size. So with constant time, if our input size were to say double, but it's constant time, would runtime even change?
Say that one more time.
Yeah. So just think about O1, right? So O1 is a straight line, right? It's a horizontal line. If we were to increase our data size by 2 times, would our runtime even change? It's a horizontal line.
I mean, I guess not, but is O1 completely horizontal? I mean,
Yeah. It
okay.
is. Yeah. So O1 means regardless of how big our input size is, it's gonna stay the same. So if you guys look at this chart again, O1 is at the very bottom. It's literally a horizontal line. So if our input size were to increase by 50 times, the program would still run the exactly the same.
And that's even if you added more data to the program.
Yep.
So irregardless,
Yep.
it's going to, well, so, okay. I guess in reality, it might take like a millisecond longer for it to run to process the data, but
Yeah.
or am I right on that?
Yeah, I guess you could say that, but overall, kind of big picture, like if you look at it, it's still going to run the same.
Yeah.
Yeah. And then if you look at O of n, this is the O of n line, just the line that like cuts it diagonally. Let's say that we increase the elements by 2 times, then or if we increase the elements by 2 times, then the number of operations would also increase by 2 times, right? It's a linear relationship. Yeah. So hopefully that makes some sort of sense. Again, if you guys have any questions or like are confused about anything, feel free to interrupt me, because this is like brand new stuff. All right, so we're gonna get into some practice problems and hopefully you guys answer. besides Chase. Chase, I love your input, but yeah, yeah. Again, this is going to be confusing because it's your first time getting exposed to this, but yeah. All right. So I have a couple examples of measuring runtime performance. So this first example is a simple print statement, right? It just says print hello. It's not really much of a program, but I guess it is a program, right? So what do you guys think the runtime of this program is?
Probably
Oh.
1.
Yep, it is 01. That's completely correct. Yeah.
So
Present.
01, that's like the actual answer. I thought I was like
Yep,
the average essentially.
Yep, that's the average. In this case, it's the average, best and worst case, because there's not much you can really do with print hello. You know?
Okay.
Yeah. I think you guys are starting to get it. Kind of. It's gonna get a little more confusing in the second, or in more examples, but yeah, but nice. Good job on the first example. How about example 2? So this is just assigning the variable x to the string hello and then printing x. It's a little more complex. So what do you guys think?
Would it still be 01?
Okay, yes, it would be. Nice. Okay. Good job. Good work.
But the time complexity would be higher on this one. I know we haven't gotten to that, just
Yeah.
asking, because we're committing something to memory. Okay.
So what we're measuring right now is the time complexity.
Sorry, space complexity.
Oh yeah, space complexity. Yeah, there's usually when you're seeing stuff like this, space complexity usually comes with a data structure. So if you guys think about an array has a certain amount of memory that it needs to occupy, right? So I guess later on you guys are gonna see that. But yeah, good job, Preston. Yeah, this is also 01. Okay. So now this is a little more complex. It's basically just a if else. What do you guys think for example 3? Basically saying if A is greater than B, return true, else return false.
Would it be 02?
So, oh yeah, a good thing to note is that O of 2, so let's say for example, we have ON, so I'm gonna put this in chat just to better visualize it. We have O of N versus O of 2N, right? Oh yeah,
Oh,
good
so they're
job.
always O of N, and then 2 is just like a multiplier.
Yeah, it's just a factor. It's just a factor. So O of N realistically is the same as O of 2 of N. Same case for this. You said O of 2, but it's really O of 2. It's really just O of N. O of 1, right?
Gotcha. Because that's
Yeah,
the same, isn't it? Because that's
it
the
is the same.
average.
It is the same. Yeah. So if you guys think about it, don't think of factors as like anything significant. Think about the N involved. Think about the input involved. Yeah.
Okay.
So if you have a case of like O of N or O of 2 of N, it's all the same thing. It reduces down to O of N. But in this case, yeah, it would be O1. Good job, Diz. And then, okay. This might trip you guys up. Example 4. Oh, what happened to example 4? Whoa. Okay, example 4. For value in data, print value. So this is a for loop, right? This is basically going each value in the array or vector, and it's printing it out. Yep, Diz, O of n. Would you care to explain why it's O of n?
Sure, you're gonna do that one operation that's print value, so that's O of 1, but you're gonna do that for every single value in data. So it'll scale linearly with data. So it doesn't matter if data's 100, it'll do it 100 times. If data's 10,
Exactly.
it'll only do it 10 times. So for one input, you have one output.
Yep, exactly. So just to kind of rephrase that, this print value is O1, right? As we can tell by example 1, it's just basically print hello, right? So we're printing the value. That's an O1 operation. But because it's in a for loop, that's for value in data, we're doing that n times. We're doing that, I guess, data times, right? So n is just an arbitrary number, right? So basically what we're doing is saying, pulling up the chat, is 1 times n, right? We're doing this print value 1 time, or for each, okay, this print value is O1, but we're doing it n times. So that equals O of n. Does that kind of make sense?
Yeah, that makes sense.
I think so.
I think it'll make more sense too once we have two separate functions running,
Mhm. Yeah,
and then we'll find out what that is.
yeah, for sure. And then we're gonna see kind of more examples of this. So yeah. Okay. This is weird. And I don't really like this example that much. But yeah, okay. So what this does, it's a for loop, and we're going over the length of n, right? Length of the input. But instead of going it over each one, right? We're skipping by 3, right? So it's a little bit different.
Starting at 0.
Yep, it's starting at 0, right? So think about, okay, so a vector, an array, in Python and most other languages, I think all languages, the 0 is basically just saying, I'm pretty sure, start from data 0, right? Start from the first element in data, right? And
Yeah,
then,
from the index.
yep, and then the second argument is saying to the length of data, to the length of the array, right? And then the third argument is saying jump 3 steps each time instead of jumping 1 each time. So this is, I'll tell you guys this, you probably won't get it because this is a new time complexity. So I think I'll just say it. This is O log n.
Why
Right, so
log?
yeah. So O log, why is it log? Okay, yeah. Good question, Preston. So basically you can think of log n. I don't really like this explanation, but online it says when the input size is decreasing each time. Which I don't really like the explanation, but think of it as, this isn't always the case, but think of it as kind of when it's not decreasing by 1 each time, right? So linear would be in a for loop wise, 5, 4, 3, 2, 1. Right. I found this online, Diz, so maybe it is O of n, but it could be. I don't know. Okay, well, we'll just say it's O of n then. Honestly, I don't like this example. We can go to this binary search example, which is probably better. It's a lot more complex, but I do like that example more. Okay.
I'll
If
be
you don't
honest.
mind, yeah,
go
go ahead, Chase.
I was gonna say I am probably the biggest math dummy here, but the whole like O of 2 in is still in, that doesn't compute in my brain, because you know, to me, I look at that and I say, well, whatever in is, it is being multiplied by 2.
So
And
you're saying it can't be equal then, pretty much. You're saying how can we just simplify O of 2 of n and then O of n? Is that what you're saying?
yes, that is
Yeah.
what I am asking. Yes.
Yeah.
That's-
Yeah, so that's a valid point. And that actually comes up sometimes. So sometimes we say, also thanks Diz for providing context. But yeah, so that's a great point, to be honest. So we can't always say that kind of O of n equals O of 40n, right? That's a little ridiculous. You know what I mean? But it is technically still a linear relationship, right? So when we say O of n, it just means it's a linear relationship. But then again, this O of n is still going to be faster than O of 40 of n. So sometimes we say this is a higher magnitude, kind of, right? This has a bigger factor, so it's going to be slower. So sometimes the factor does matter in these cases. So that's a completely valid point. But basically what we're saying when we say like O of 2 of n is equal to O of n, we're just basically saying it's a linear relationship. Is that like an okay explanation?
Yes. However, I don't say, no, just keep trucking. And
All right. All right, yeah, sure. Okay. Yeah, I didn't like the last example, but I think binary search is better. I think it's kind of useless to kind of show you the actual algorithm because it doesn't make sense. But basically what it does is basically it starts at the middle of a vector. So binary search is used to find a number, I think. Yeah, it's a searching algorithm, searching for a specific number. So basically the first step is to look in the middle of the vector, right? And also it has to be sorted. Keynote, this has to be a sorted array, just as a keynote. So we have a sorted array here, right? And basically the first step is to say, let's go in the middle of the array. So let's look at maybe 16, right? So because it's sorted, and we know that the middle is less than our search number, which is 23, we can cut off half of the input, right? So we can cut off 2, 5, 8, 12, and 16, basically.
bisection, correct?
No, basically what we're doing is basically just saying, because we know that our search number is greater than the middle, we don't need to look from left to the middle. Because we know it's going to be on the right side now. Right side of the sorted array, right?
Does it do
So
this
that's-
automatically?
Well, basically we had to create an algorithm for it. So if you guys check here.
I
Yeah,
thought this was like a built-in function or something that I haven't seen.
it is a built-in function in C++. That's where like my main domain is. But yeah. But this is the algorithm. And then it does this each time. So basically, after we cut off this left side, so from like 2 to 16, then we check the middle of the right side array now, right? So we check from 23 to 91. So the middle of that is 56. Okay, that's greater than our search number. So we can cut off 56, 72, 91, right? So it's basically cutting the input size by half each time, if that makes sense. So that's why it's log n. Log n, I like to think of it as when we're kind of cutting the size by half each time. I don't know. It's kind of a bad definition, but hopefully that
Cutting
makes
like the
sense.
size of the array in half
Yeah.
each time. Okay. So say it's only, so we take that half, right? At 16. then is the next step to look in the half of that half and to see where we're at. Is that where am I getting this right?
Yeah. Yeah, I think that's correct. Yeah,
The new
so
array technically would start at 16, or would it start at 23?
I think it would start at 23. I'm pretty sure, but
Okay,
don't
that
quote
would
me
make
on that.
most sense.
Yeah.
And then it would go 23 to 91, check that
Yep.
half, and they're like, okay, well now we have to restart from here in this shortened array to find our number that we're searching.
Yep. In that 23 to 91 array, we will do the middle of that array, so 56, right?
Yeah.
And then so we basically just keep on cutting the array by half.
Okay.
Does that make sense? I think
No,
it's a
it definitely
pretty
does. That's a smart way of thinking about it rather than just doing a for loop through everything.
yeah. But yeah, so that's binary search. Hopefully that makes more sense than the past example. But that's log n. All right,
And
cool.
and that's not bisection.
I guess you can think of it as what's your definition of bisection? Like basically we are cutting it by half each time.
Exactly. Like I was pretty sure that that's what it was, but so I just
Yeah.
had to look it up here, and I'm pretty sure that at least that operation is bisection, but that's an aside.
Yeah, that's why it's called binary search, because we're only searching half the array and then we're passing back that half and checking half that. So you're bisecting it each step of the way.
Right. Okay.
Yeah, hopefully this example makes sense. I think it's a pretty intuitive algorithm and like it makes sense. But cool.
But why is that called log? What's the reason for log?
Yeah, so I guess log n normally, if you think of a log function, it kind of looks like, exponential looks like this, right?
Yeah.
Like kind of a slope, like a slide, but log n is like the opposite, like this. So it's like kind of dividing by half each time, if that makes sense, or dividing by whatever each time, right?
Okay.
Yeah. So does that make sense?
Yeah, I get what you're saying.
All right, cool.
I was trying to put that puzzle together in my head, but that really explained it.
All right, cool. Again, I'm not the biggest math guy. I did not do well in discrete math, but we moved past that. We soldiered on. Okay. All right. Let's go into more kind of complex examples, I guess. And hopefully you guys are kind of not enjoying it, but like it's kind of interesting. Hopefully, I don't know.
I'm enjoying it. I don't get the math, but yeah, it's fun.
Okay.
I'm learning something.
Okay, that's a start. All right. All right, let's look at this more complex example, right? So what we have is a nested for loop. And I'm sure that you guys already know what a nested for loop is. So let's dissect it, right? So it's saying for x in data, right? So that's going n times, right? And then the next and then it's a nested for loop. So it says for y in data. So that's also going n times, right?
Yeah.
Yep. So then, and then we just have a simple print statement. That's O1, right? We figure that out. So let's think about this. I'm going to start from the bottom. We have a O1 statement. Then we have a O of n kind of operation. Then we also have and then we have another O of n statement. So what do you guys think that is?
Exponential.
Yep, exactly.
No way.
Yeah, quadratic, I guess. Yeah,
I didn't call
quadratic.
it
Yeah.
that.
Yeah, so technically it wouldn't be called exponential, but yeah, I know what you mean.
It's
So
called
technically,
quadratic. Okay.
yeah. Oh yeah, awesome. Yeah, good job. Sorry, I haven't been seeing your message, but yeah, n squared is the correct answer. So it technically wouldn't be called exponential because n squared is different than n cubed and so on, right? We want n squared more than n cubed, if that makes sense.
Yeah.
So in this case, it's n squared. Example 7 is n squared because we're doing n times 1, which is n squared. Make
Gotcha.
sense? Cool.
So it would be
Jefferson.
O of n squared.
Yep, it would be O of n squared. That is correct. And also good job, Austin. All right, I can't see this full example. All right, example 8 is meant to trick you up or like trick you. So hopefully you guys don't get tricked. We'll see though. Okay, let's see what this says. So first we have a for loop for x in data print hello, right? So we know what that is, right? So that's n, correct? We know that's n. But then we
Yeah.
have a nested for loop, right? So we have for y in data, for z in data, print goodbye. So we have a for loop, outside for loop, but then we have a nested for loop.
So would it be like O of n for the first function plus O of n squared?
Sheesh, I was killing it. Yeah. Yeah.
Because it's
That's
just time, right? So you just add the time together.
exactly. So it would be kind of like this. So O of n plus n squared.
Yeah,
But
that'd be like the simplified version.
but in time complexity, the higher magnitude overtakes the function. So technically, it would be O of n squared. This would be like a simplified version, right? Because the O of n squared dictates how slow this program is going to run, if that makes sense, right?
Okay.
The higher magnitude overtakes the O of n. But your answer is like more complex, I guess. But yeah, does that make sense to everyone? The higher magnitude overtakes and dictates the program pretty much, right? Hopefully that makes
Yeah.
sense to everyone. All right, cool. All right. Okay, finally, we can move on to the actual topic of this lecture. Okay. So has anyone heard about data structures before? Or is it better for me to go in slideshow mode? I don't know. What do you guys think? Or is it better like this? You think so? Okay, I'll do that then. Have you guys heard of data structures before? Yes?
Yep, I've heard of them.
Okay, that's a great start. That's a great start. And you guys have used this before, you know, lists are data structures, arrays are data structures. I think we've talked about key associated or like associative, like key value kind of, those are all data structures. And data structures are just like overly complex term to like, it's a barrier of entry to like people that want to get into CS. But you guys have all interacted with them. So there's no need to be intimidated by the term. And then how about a algorithm? Have you guys heard that? I mean, you probably, obviously.
Yeah. I
Nice.
just don't. We'll see how it compares, I guess.
Yeah. So I guess the relationship would be that not all the time, but algorithms are used on data structures, right? So when we looked at the binary search algorithm, the data structure was the array, right? The algorithm was the binary search algorithm. So it's not really a correlational relationship, but yeah. Pretty much an algorithm is just kind of a a recipe, a set of instructions to do a task. It's like, yeah, it's a cooking recipe, pretty much. All right. Time to get into our first data structure. And I think you guys have already interacted with this before, but it is Python dictionaries. Do you guys, have you guys used this before?
Just Python
Yeah.
dictionaries.
Yep, Python dictionaries.
Yeah.
Cool. Yeah, so in C++, life is a lot harder. That's my domain. But yeah, dictionaries. I'm used to calling them hash tables. So if I call them hash tables, just know that it's the same thing as a Python dictionary. And then if you are curious about the theory behind dictionaries and hash tables, I'm more than welcome to, but it's just going to turn into a ramble. But all right, so you guys already have experience with it, but a dictionary is just a collection of key value pairs, right? So what makes it so powerful, right? Dictionaries are very good at finding an element. It's actually O1. And you might be confused as why, but that goes into the theory. Pretty much it just uses a function to find the location in the array. So the underlying data structure, it uses like a vector array, and then it uses a function to find its location in the array. And that function is O1. But anyways, that's a little too confusing, but pretty much what makes it so powerful is that for searching an element, it is O1. And in like putting in an element, so inserting an element, it's pretty sure it's O1. All right. So typically when a question is based around searching, a dictionary is pretty good. And then a note, this is an example of sacrificing memory for runtime. So typically dictionaries use an access of memory. It uses unused space, right? And I didn't want to get into the theory, but I'll do like a short like ramble. Pretty much, like I said, the underlying kind of data structure is a vector or array, right, for a hash table. And we reserve a certain amount of space in that array, right? But let's say we only put 3 elements into our hash table. So then let's say that means that there's only 3 out of, maybe 10 slots in the array that we used. So that's why there's sometimes unused space in a hash table, and that's why typically dictionaries use a access amount of memory. But yeah, that's a short ramble about why. Okay, let's get into some syntax. Best part. Okay. So yeah, creating a dictionary. So this is just dictionary name, and then we do braces, and then the left side is the key, and then the right side is the value, right? And I guess in Python, you can have different types. So as you can see, this is string, or Branford is string. But third one is year 1964. So that's a string and then an int or number or whatever. But yeah.
It's int in Python, but yeah, same.
All right, cool. And then to return each element in a dictionary, I'm pretty sure this is to retrieve all elements in a dictionary. It's dictionary name dot items. So that's dot items is just a method or a function that's built into Python to make life easy. But yeah. Okay. And then to check if a key exists, we say if model in this dict. So that this means if key exists in this dictionary, right? Model, we're checking if the key model is in the dictionary. All right. Hopefully this makes sense.
Like the strict. Hold on, let me read it before I.
So you're just checking to see if model the key exists.
In a so this dict is a dictionary name,
Yeah.
is our dictionary. Model is the key that we're checking. Yeah. Hopefully that makes sense. Okay. And then inserting a new key value pair. So dictionary name, brackets, key equals value. Now, I guess that's one way of inserting, but yeah. Okay, and then I made it was a little excessive with all these caps. It's a little excessive. There's CS is not that crazy. um pretty much you don't want to check if a value exists by using this method. I guess that's a little confusing, but basically by default, a dictionary will create a new key value pair in the dictionary if you use a syntax. So if you want to check if a key exists, you want to use this method right there, if key in dictionary name. And then how to make an empty dictionary is just dictionary name equals braces. Okay, we're gonna go into our first problem. So would you guys want to try this problem out? I feel like I'm kind of just like throwing you overboard and then like not giving you like any
Send
help.
it. Send it, dude. Let's go. Let's go.
Okay,
Let's
I
go.
think you're doing good, Joel.
Yeah, I
All
do
right.
too, man.
Thanks guys.
Don't be hard on yourself.
It's been
Okay.
a long time since I messed with Python too, so this is good.
Yeah, I agree.
Great. Okay, so I sent the problem in chat. Okay. Okay, I'll ignore that message by Diz. Yeah, let's send it. I'll give you guys how much time do you guys want on this? What do you guys think? 5 minutes, 10 minutes?
Yeah, like 5. I
Okay.
don't know. Yeah, why not?
Yeah, 5 minutes. Yeah, go take a crack at it, see how it goes.
Don't forget to change it to Python.
Oh yeah, my bad. Also a tip, it's honestly better to probably use a set on this problem instead of a hash table, but a hash table also works. Hash table kind of makes it a little confusing. But yeah, just keep in mind maybe a set is a better way of doing it. But anyways, good luck. May the best one win.
After reading that, I'm not sure that you could even do this with a set, because with a set you can't have multiples of the same thing.
Is like maybe 2 or 3 minutes fine? Yep.
Like 2 or 3 more minutes.
Yeah, 2 or 3 minutes fine.
Yeah. Give me
That's
a
good.
couple.
All right, yeah, sounds good. You can also do this solution by using an array or vector. But yeah, there's gonna be different time complexities, but we'll see. All right. How did everyone do? Austin, were you able to complete it?
Yeah, I did it. Using like a built-in kind of function, so it's kind of cheating.
Or what function is it?
Just dot count.
Oh, okay. Nice. The cool thing about coding is that there's a bunch of different solutions that you can do. Did you use a dictionary?
No,
Nice.
it was presented in like a list, so I just used
Okay.
list.
Yeah, nice. Yeah, there's a bunch of different solutions. I think that's what makes coding interesting, that you can always have like a million different solutions. Can I move on to solutions or like possible solutions?
Yeah, let's see him. I forgot the syntax in this shit.
That's fine. I always do too. Okay. All right. Let me put this in slideshow mode. Okay. Okay. Let's check this out. All right. This is the hash table solution that I came up with. Again, hash tables are a little weird for this problem, but it works. So let's walk through it, right? So first we have I make an empty dictionary called hash table, right? And then I go over the nums list or array or whatever, right? And then I say, if the element is in the hash table, then return true, right? Contains duplicate, basically saying if there's at least 2 elements that are like the same in a list, then return true, right? Otherwise return false. So what I'm saying is, if the key value is in a hash table, return true. Else, this is the weird part. Put in kind of the key value pair inside the hash table. It's weird because what I'm doing is putting the key and the value as the same element, which is strange. So I
Can you
see.
just have it else false though?
Hmm?
Couldn't you just have it as else false?
Yeah, so that's why we can't do that, right? So let's imagine the dictionary is empty in the beginning, right? So there's no elements in the dictionary. And then we iterate through the list, the nums list.
Okay.
So let's think about this. We're going into the list now, right? And we're checking the first kind of element in the list. If X is in hash table, okay, well, the hash table is empty. So it's going to do the else statement, right?
Oh, gotcha. So you're making another table.
We're not making another table, but we're inserting an element into the table, if that makes sense.
Gotcha. Well, technically, won't there be? So nums is another hash table, right?
Nums is the list.
Okay. And then you're making a hash table from that list.
Yeah, so I made a hash table in the beginning, right? So hash table equals curly brace. I'm creating
Yeah.
an empty table. My next step is to iterate over each element in the list, nums. That's the name of the list.
Yeah.
My next step is to say, if that element or is that element in my dictionary or hash table, correct?
Yeah.
And in the very beginning, it's an empty dictionary. So obviously it's not in the hash table. So that means that we go to the else statement. And that's when we put in the key value pair. So we're doing hash table X equals X. So we're putting in the key value pair inside it. So now it has one element in there, right? It has the element X, right?
Yeah. I get what you're saying here. So maybe I'm just reading the syntax wrong. But when you're saying hash table X
Oh yeah,
equals
yeah.
X,
Yeah, that's a
is
confusing
that
part.
giving it, because isn't a hash table or a dictionary that isn't that supposed to have a key and a value?
Yeah, so that's why I don't really like this answer, and I made it. So
Well, wouldn't it just be plus equals 1
yeah,
rather
so
than X?
what we're doing right now is actually okay, let me break this down. So hash table is the table name, right?
Yeah, I understand that part. The only
Yep.
part is this hash table X
Mhm.
equals X.
Yeah, so then we do this part, right? This part. This is the key name that we're putting in. And then the next step is we're equaling, right? X. And that's why it's confusing, because this is also the value that it retrieves. So if we were to do, let's say we want to see what the value of this is, then this operation would return X. So that's why it's confusing. The key and the value in this example are the same thing. They equal the same thing.
Yeah, why wouldn't you want it to just plus equals 1 and then we can keep track of how many of those keys or how many of those keys technically in the hash
Oh,
table.
wait, that's actually a better solution. That's actually a better solution. That's a good solution. Yeah.
I get what you're saying here, but I feel that's what made more sense to me.
Yeah.
Well, I
that
mean,
makes sense.
to be fair, I actually think yours is a better solution. Like if you're just trying to be the most pragmatic about it, because at the end of the day, we don't care how many of them there are. We just care is there more than one of the same? So
That's a fair point.
But wouldn't we just, instead of making a hash table or a dictionary, why wouldn't we just make another list or another array?
You know,
because
oh yeah, Chase.
with the dictionary, I mean, it's basically doing exactly what you're saying, Preston.
Well, in this case, if you find a 3, then in the dictionary, it's going the key value, or just like the key is going to be 3, but then 3 is also going to equal 3.
Yeah, that's why it's kind of a weird example. And I'm gonna show you a better. Oh yeah,
Wait, what?
But it definitely works for sure. It'll definitely work.
Well, okay, let's say that we have an array and it's 1, 2, 2, 3. Okay, well, let's say it's 1, 2, 3, 2. So it's all the way at the end, right? As it iterates through it, it's going to create this dictionary. It's going to go, okay, 1, there is 1 instance of 1. And then it's going to say 2, there's 1 instance of it in there so far. And then 3, 1 instance of it so far. And then when it comes to 2 again, it's going to now, not with this particular code, but
No,
it would
it
update.
wouldn't do that though. It would do, as soon as it hits 2, it's going to be 2 as the key and then 2 as the value.
Correct.
But then if it's going to, when it hits 3, it's going to be 3 as the key and 3 as the value. That's why I'm saying hash table X should equal plus equals 1 to get what you're trying to do, Chase.
Oh, yeah, okay. Yeah. No, yes, you're correct. That's correct.
But I don't think we specifically need to do that, I guess. But is another fair point, Joel. I'm not sure the syntax on that if statement. So when you're checking X, if X in hash table, is that only checking keys or is it checking values?
I think it's checking keys, right? Because if we go to our, yeah, checking if a key exists, if in this case, if X is in dictionary, so that's checking keys.
Okay, yeah, then I don't think there's a use for a dictionary here unless we're trying to keep count of how many. Sorry if I
Yeah.
confuse people, but I
No,
think
no.
that's
I appreciate the input.
a better way.
I think
Is
it's,
there, do you have another solution to this?
yeah, I have
Is
two
it a
others.
nested for loop?
I have two others. So this is the first solution. Oh yeah, also question, what do you think the runtime of this is?
I'm going 01.
Okay. That would be really good. I would really love that solution. But let's think about this. So we make a hash table, so that's a 01 operation, correct?
Yeah.
And then I think you forgot this part, maybe. Then we have a for loop, and then it iterates over the list. And that's a O of N operation. And then the rest of this stuff is O01, right? So this if else, this checking if it's in the hash table, that's O01. String true is a O01, else statement is a O01. Inserting into a hash table is also O01.
So it would be ON since that overrules it.
Correct. Yep.
Okay.
Yep. All right. So runtime is O of N. And then here's, I think the next solution is a pretty good one, and I'm pretty happy with the solution. Yeah, but Keynote realistically a set would be better. And then a set is like a hash table, but its actual value is used as its key. So it's kind of like a key value, but you'll see. All right. Also, it's pretty interesting to see, but leak code gives kind of actual like runtime and memory analysis. So you can see the runtime is not the best, but also the memory is really bad, right? And we talk about how hash tables are really bad on memory, right?
Yeah, because it's just taking up all the empty space, right?
Correct. Yeah, nice. All right, let's check the next solution. This is a pretty clean solution. So this is using a set. So let's see, the first line is creating a empty set. And then we iterate over the list for x and nums. And then we check if x is in the set, return true, else we add it to the set or return false.
What's a set again? Is that like an array?
Yeah, a set is pretty much like, you can think of it as a hash table, I think, but there's not really a key value associated with it. You can check if something's in it by just saying like if x in hash set, right? So that's why it's so handy. Because its
So it's-
actual value is its key. Yep,
Sets are no duplicates, right?
I think so, yeah.
Tuples as well, I think.
Let me, yeah, did I put more information about set? I can, can one of you guys put more information about sets, Python sets? But yeah, I'm pretty sure it's no duplicates, so that's why it's kind of handy for a question like this. And I think it's a lot cleaner, right? Because it's like, it's less dumb than this than this statement. But what do you guys think the runtime of this program is?
One second, I'm reading. Someone else answer.
I mean, it seems like the same thing, except we're using a set instead of dictionary.
Yeah.
Is it not?
Yeah, pretty much. Oh, yeah, pretty much. It's oven. It's also oven. So
But the
I guess,
memory is better.
yep, memory's better. And Chase, like you brought up, O of n is not always the same. And you're about to see that in the runtime analysis. Let's check it. So it's way better in runtime comparatively, right? So let's see. Beats 28.45, beats 62.78. So it's way better. And also the memory is significantly better as well, right? Beats 5.34, beats like 50%, right? So this solution is just better. It's just better in all ways. All right, let's move on to the array/vector solution. Just for some context, this is my kind of way of kind of solving it using array, but basically what this nums.sort function does is that it goes over the list and just sorts it by least to greatest. It's just a sorting function. So hopefully that makes sense. And for context, I'm pretty sure, what is that? Probably O of n squared. I don't know, whatever.
Nums.sort.
Oh, context, it's n log n. N log n.
This one is?
The sort function by itself is n log n.
Okay.
By itself, yeah. And then basically what this is saying is that we sort the list. And then because if we're sorted, then the thinking would be that two numbers that are equal should be next to each other, right? Hopefully
Yeah,
that makes sense. Yeah, so that's basically what we do. All right, given the context that nums.sort is n log n, what's the runtime of this function?
is this one O of 1?
That would be really good. But, all right, let's think about this. So it can't be O of 1 because this nums.sort is already n log n.
So that's
Right.
bigger.
Yep, n log n. O of 1 is the best. It's the lowest it could be.
Oh, okay.
Yep. So nums.sort n log n, and then we have a for loop. That's n. And then we have a bunch of O1 operations. So then we have n log n plus n, right? So n log n trumps it, right? N log n is greater than n. So then this runtime is n log n, I guess. But you're about to see that the runtime and memory is, the memory is really good. But the runtime is not the best. So typically, when you have a vector solution, the memory's gonna be like amazing, right? Because for vectors, I mean, not really, but you use the space that you use, right? There's no extra space. There's no unused space. Runtime is typically going to be slower because you have to usually iterate stuff. Or appreciate the, I don't know what that is, but appreciate it, Chase.
It's just random, like the differences between set, dictionary, and tuple
Gotcha.
data types in Python.
All right. Yeah, so that's this solution. Oh my God, I have another, I had 4 solutions for this one problem. I'm pretty proud of myself. Anyways,
That's
right.
what I was working on. I swapped to this solution
Mhm.
after I was like halfway through the other one.
All right. So let's see. Let's see this. I think this is the final thing that we're gonna do today, probably, because I think we did do a lot. But let's check the solution. So we go over nums, right? So that's I in range. Then we do for j in range. So that's another n operation, right? What do you guys think?
That'd be n squared, isn't it? If it's
Yep,
nested.
it would be n squared. So because it's n squared, the runtime is gonna be worse. The time complexity of the solution is gonna be worse. What do you guys think? So Preston, I know that you're working on this solution, and it is a good solution, but I think this is a good example of why we have all these extra data structures, right? Because it
Yeah.
does make runtime better in some cases. And this is a example of like data structures like a hash table, but more so a set, performing drastically better than this.
Oh, definitely.
Isn't this just a convoluted, purposely convoluted, but convoluted version
Solution.
of what solution that I posted? If the length of numbers is equal to the length of set numbers, return true, else false. That's what we got going on here, right? Except we're like
Um,
double iterating.
let's see,
Like,
see what I wrote. I think I'm checking for each element. So I'm basically just doing this. Let's say this is the start of the array. and I'm looking at this element specifically, I'm checking, is this element equal to this one? Is this element equal to this one, this one, this one, this one? And after that
Oh,
for loop's
yeah.
done, then we move on to this one, the next element.
Oh,
Is this
yeah,
equal to
that's-
that, yeah. So it's
that-
very
yeah.
convoluted.
Very.
But yeah, I think a pretty good array vector solution is to sort it first. Because it is better than n squared. But I was going to take a look at this, but I feel like it is running pretty long. But yeah, so this is another example, and for context, a hash table is, I think, the best solution for this. So it's not like the past example contains duplicate. And two sums a very famous kind of LeetCode problem. I don't know if you guys have heard of it, but it is like pretty famous, and it's a good like kind of intro problem to like hash tables and stuff. And I did leave my solution there, and it's runtime analysis. And then after you complete that, I put in some other problems, some like general like array/vector problems. For context, this problem is really convoluted and it's like kind of annoying to write. So if you guys don't want to do that problem, that's perfectly fine. But I think these problems are pretty good to like kind of look over again. If we do another kind of lecture, I guess our next stuff that we would talk about is more data structures, so stacks, queues, and then recursion. But yeah, I think I can just put this problem in chat. Chat there, and then I think I did. Oh, should I just? Oh, I'll share my GitHub link again. But hold on, I put it somewhere. Yep, I'll put it right here. Okay, those are my slides and stuff where you can find the extra problems to practice. And then I guess the problem that you should do first is the two-sum, because that goes over hash tables and stuff. I think the solution is pretty cool too. But yeah, I think that's everything for today.